Hello everyone, welcome to my channel GVS Chem. In this video, I am going to revise the electrochemistry up to half of the lesson. This video is useful for the students preparing for board examination. Please subscribe to my channel, like, share and comment my videos. Electrochemistry. In this video, I am going to explain electrochemistry in short, that is for the preparation for board exam. Conductors are of two types, that is electronic conductors, electrolytic conductors. So electronic conductors, electrolytic conductors. Electronic conductors, electrolytic conductors. Electronic conductors means pass electricity in the form of electrons. In the electronic conductors pass electricity in the form of electrons, whereas electrolytic conductors pass electricity in the form of ions. For example, copper, silver and other metals. Whereas here electrolytic conductors, aqueous solution of sodium chloride, aqueous solution of copper sulfate. So here when sodium chloride is dissolved in water, we get Na plus Cl minus. So in the form of ions, they pass electricity. Now factors on which electronic conductance depends. One is nature and structure of the metal. Nature and structure of the metal. Then valence electrons, number of valence electrons. For example, sodium has one valence electron, magnesium has two valence electrons, copper has two valence electrons. Right. Then temperature. If temperature increases, electronic conductance decreases. If number of electrons is more, electronic conductance is more. On the other hand, factors on which the electrolytic conductance depends. One is nature of the electrolyte. Then size and charge of ion. If the charge of the ion is more, electronic conductance is more. Right? Size and charge of the ion. Number 3, temperature. If the temperature is more, electrolytic conductance is more. That is, when the electrolyte is heated, the energy increases, therefore the movement of ions increases, the mobility of ions increases, therefore electrolytic conductance increases. And solvation of ions. Then next, viscosity of the solvent. So these are the factors on which the electrolytic conductance depends. Now let us learn some definitions. Current in a conductor. Conductor means electronic conductor. Current in a conductor is directly proportional to. Current in a conductor is directly proportional to the potential difference applied. At a constant temperature. So I is proportional to V. I is the current, V is the potential difference. R, I equal to V by R, where R is a proportionality constant known as, R is called resistance of the conductor. So unit of resistance is ohm. 1 ohm equal to 1 volt by 1 ampere. 1 ohm equal to 1 volt by 1 ampere. That means if a potential difference of if a potential difference of 1 volt across the terminals of a conductor allows a current of 1 ampere, then the resistance of the conductor is said to be 1 volt, 1 ohm. Now, resistance is directly proportional to the length of the conductor. Resistance is directly proportional to the length of the conductor and inversely proportional to the area of cross section of the conductor. Area of the cross section of the conductor. Therefore, R is directly proportional to length of the conductor. R is directly proportional to 1 by A. Inversely means reciprocal of area of cross section. R equal to rho into L by A, where this is called rho. Rho is called specific resistance. So, resistance of the conductor is directly proportional to the length of the conductor and inversely proportional to the area of cross section. Therefore, R equal to rho into L by A, where rho is a proportionality constant known as specific resistance. So, here R equal to rho into L by A. R, bring this to this side, RA by L equal to rho. Now let us find the units of rho. Therefore, units of rho are rho equal to RA by L equal to unit of resistance is ohm, unit of area of cross section centimeter square by centimeter. Therefore, this is equal to ohm centimeter. Unit of specific resistance or resistivity is ohm centimeter. R ohm meter. Now, 1 ohm meter equal to say this is 1 ohm into 1 meter, how much? 100 centimeter. So 1 ohm meter equal to 100 ohm centimeter. So 1 ohm meter equal to 100 ohm centimeter. Or this is also written as, this is the symbol for ohm. Now, in the same manner, let us find 1 ohm centimeter equal to how many ohm meters? Now here, this is 1 ohm. 1 centimeter can be written as 1 by 100 meter. This is because 1 meter equal to 100 centimeter. 1 centimeter equal to 1 by 100 meter. So keep this in mind. So using this, we get 1 ohm centimeter equal to 1 ohm into 100, 1 by 100 meter. This is equal to 1 by 100 means this is 0.01 ohm meter. This is also written as 0.01. This is a symbol for ohm. So these are the units of specific resistance. Now let us have the another definition. Conductance. Conductance means it is a reciprocal of resistance. Conductance is the reciprocal of resistance. So conductance is denoted by the letter G. So G equal to 1 by R. G equal to 1 by R. So what is the unit? Unit of G equal to, this is 1 by R, that means 1 by ohm. 1 by ohm can be written as ohm inverse. R ohm inverse in this manner. Ohm inverse is also referred as Siemens. Other unit is Siemens. 1 ohm inverse equal to 1 Siemens. It is denoted by S. S is the symbol used for Siemens. Now let us learn another definition, that is conductivity or specific conductance. Conductivity of a specific conductance is the reciprocal of resistivity. Reciprocal of resistivity. What is the resistivity? Rho. Therefore, conductivity K, this is K, this is kappa. Kappa conductivity is equal to 1 by rho. Rho means what? Just now we studied rho equal to RA by L. Therefore, 1 by rho equal to 1 by RA by L. This is nothing but 1 by R into L by A. 1 by R into L by A. Right. Here now the units of K, conductivity. Now apply the units here. 1 by ohm into centimeter by centimeter square. This is nothing but ohm inverse centimeter inverse. Ohm inverse is nothing but Siemens. So Siemens centimeter inverse. Siemens centimeter inverse. Or another unit is Siemens meter inverse. Siemens meter inverse. Now let us convert the Siemens centimeter inverse into Siemens meter inverse and vice versa. So this is 1 Siemens centimeter inverse equal to 1 Siemens by 1 centimeter. Centimeter inverse means 1 by 1 centimeter. This equal to 1 Siemens by 1 centimeter. How do you write? 1 by 100 meter. This is nothing but 100 into 1 Siemens by meter. This is nothing but 100 Siemens meter inverse. Therefore, 1 Siemens centimeter inverse equal to 100 Siemens meter inverse. In the same manner, 1 Siemens meter inverse equal to 1 Siemens by 1 meter. 1 Siemens by 1 meter equal to 1 Siemens by 1 meter equal to 100 centimeter. So 1 by 100, how do we write? This is 0.01 Siemens centimeter inverse. So 1 Siemens meter inverse equal to 0.01 Siemens centimeter inverse. So this is the conductivity or specific resistance and its units. Now conductivity of an electrolytic cell can be found by using a specially designed cell. So by using a specially designed cell, electrolytic conductance can be found. Now here the electrolytic cell is kept here in the Wheatstone bridge. This is Wheatstone bridge. So here this is the electrolytic conductor, and R1, R3, R4 are known resistances. By using the principle of Wheatstone bridge, R2 equal to R1 by R4, R1 into R4 by R3. So the electrolytic conductance can be found in this manner. Now K equal to 1, we discussed just now, K equal to 1 by R into L by A. What is R? 1 by R equal to G, that is conductance. L by A is equal to G star. G star equal to cell constant. G star equal to cell constant. Now let us see the molar conductivity. Molar conductivity of an electrolyte is the conductivity of 1 molar solution when entire solution is kept in between two electrodes unit distance apart and having a cross section of large enough to accommodate the entire solution. Therefore, lambda m is molar conductivity. So lambda m molar conductivity is equal to K by C. What is K? Conductivity. K
K is the conductivity by C concentration in mole per liter. Concentration in mole per liter. This is equal to lambda m equal to conductivity. What are the units of conductivity? K, the unit of conductivity is Siemens centimeter inverse into 1000 centimeter cube by liter by molarity mole per liter. So how do we write this? So this is nothing but K into 1000 by m. K into 1000 by m. Now units of molar conductivity. Units of lambda m, that is molar conductivity. What are the units of K? Siemens centimeter inverse, and molarity mole per centimeter minus 3. This is nothing but Siemens centimeter minus 1 into centimeter plus 3 into mole minus 1. This is nothing but Siemens centimeter square mole minus 1. So this is the unit of molar conductivity. Now let us see the variation of conductivity and molar conductivity with concentration or dilution. Now, what is conductivity? Conductivity is nothing but conductivity or specific conductance refers to the conductance of 1 centimeter cube of the electrolyte. So, conductivity means conductivity is the conductance of 1 centimeter cube of electrolyte. Right. In 1 centimeter cube, say certain X ions may be present. If 1 centimeter cube is diluted to 10 centimeter cube, that is 9 centimeter cube of water is added, the number of ions does not increase. Therefore, number of ions in 10 centimeter cube is also X. Now number of ions in 1 centimeter cube equal to X by 10. So number of ions decrease as dilution increases, number of ions decrease. If number of ions decrease, conductivity decreases. Therefore implies conductivity decreases. Therefore, if dilution increases or concentration decreases, conductivity decreases, because as dilution increases, number of ions per centimeter cube decreases, therefore conductivity decreases. This is about variation of conductivity with concentration. Now let us see the variation of molar conductivity with concentration. To understand the variation of molar conductivity with concentration, observe this table.
In the table, molar conductivity, that is lambda m, in Siemens centimeter square mole minus 1 of electrolytes at 298 K with different concentrations. The concentrations are 0.1 m, 0.05, 0.02, 0.01, 0.005, etc. And here HCl, hydrochloric acid, sodium hydroxide and NaCl, they are strong electrolytes. If you observe the molar conductivities of these strong electrolytes at different temperatures, different concentrations, the increase in molar conductivity is very less. The increase is very less. And here also, this is 238, 249. And here 106.74, 111.06. In case of weak electrolytes like acetic acid and ammonium hydroxide, see here the molar conductivity at 0.1 molar, 5.2, and at 0.5 it is 7.4, and at 0.2 it is 11.6. So here the increase in molar conductivities are very high. See here, At 0.02 m 34, at 0.01 m it is 46.9. So molar conductivities of weak and strong electrolytes increases very less, and here it is increases very high. The reason for this is in case of strong electrolytes the dissociation is complete, right, but the volume is less. So in lesser volume ions cannot move. The space for mobility, the space for moving the ions is very less. On increasing the dilution or decreasing the concentration, more volume is available for ions to move from one place to another place. Therefore the molar conductivity increases to very less extent. In case of strong electrolytes, in case of weak electrolytes, the dissociation is very less. As concentration decreases or dilution increases, more amount of substance, more amount of solute dissociates, therefore more number of ions are available. Keep the point in mind, in this case ions are not increasing, only volume is increasing for mobility of ions. In this case, in case of weak electrolytes, number of ions increase as the dilution increases. Therefore, in both the cases molar conductivity increases, but with different reasons.
So a graph is drawn between lambda m and square root of c. Lambda m is the molar conductivity, square c is the concentration. So the graph is obtained in this manner. This is the graph. So here this is the weak electrolyte CH3COOH, and this is KCl. So this is strong electrolyte, this is weak electrolyte. Whereas here this is C to the power 1 by 2, that is square root of concentration, and this is the lambda m. So here concentration increases. So as we move towards this right side, concentration increases. As concentration increases, molar conductivity decreases. As concentration decreases, molar conductivity increases. Therefore, we extend this graph with a dotted line. Therefore, when the graph of KCl is extended, when the graph of KCl extended, it meets y-axis. It meets y-axis. As it meets y-axis means the concentration becomes 0 or dilution increases to infinity. This shows that the concentration is negligible. The concentration is negligible or infinite dilution. So wherever this graph meets y-axis, that the value here is referred as limiting molar conductivity. So the point at which the graph meets the y-axis is called limiting molar conductivity. Limiting molar conductivity or conductivity at infinite dilution, or molar conductivity at infinite dilution. And of course it is denoted as lambda naught m. This is for strong electrolytes. So for strong electrolytes we can find the limiting molar conductivity by extending the graph. Then what about weak electrolytes? Weak electrolytes, see here, from here the graph goes parallel to the y-axis. Therefore, even if you extend this graph, it does not meet. So for weak electrolytes, the graph does not meet the y-axis. Now, why this for strong electrolytes as well as weak electrolytes the molar conductivity increases, that we discussed just now. So in case of strong electrolytes, at higher concentrations, ionization is complete. Ionization is complete. In case of strong electrolytes, ionization is maximum, right? Since ionization is maximum, large number of ions are present. Large number of ions are present in less volume. Large number of ions are present in less volume. Due to this, what happens? The mobility of ions is restricted. Mobility or movement, mobility of ions is restricted. There is no sufficient space for ions to move. Not only that, because ions are very close to each other, electronic interactions also affect the mobility of the ions. Therefore, when dilution increases means large volume is available. Large volume is available. As large volume is available, ions move freely. Therefore, lambda m increases. So as dilution increases means concentration decreases. Lambda m increases because the ions move freely. Therefore, conductivity, that is molar conductivity, increases. This is in the case of strong electrolytes. Now let us discuss the increase of molar conductivity in case of weak. So, in case of weak electrolytes, we know that weak electrolytes are dissociation is not complete. So, for weak electrolytes, dissociation or ionization is incomplete or is very less. So, if dilution increases or amount of water, if dilution increases, what happens? Dissociation also increases. Therefore, more number of ions are available. As more number of ions are available, lambda m increases. So for both molar conductivity in case of strong electrolytes and weak electrolytes, in both the cases molar conductivity increases, but in each case the explanation is different, because in case of strong electrolytes there is no space at higher concentrations. So if dilution is increased, there will be more space for ions for mobility, therefore molar conductivity increases. On the other hand, in case of weak electrolytes, the dissociation is incomplete at higher concentrations. Therefore, if dilution increases, dissociation increases, number of ions increase, therefore molar conductivity also increases. Now, as we discussed previously, this molar conductivity of weak acids or weak electrolytes cannot be found. The limiting molar conductivity of weak electrolytes cannot be found because they do not meet the y-axis, as they are going parallel to the y-axis. Therefore, in an indirect method, lambda m infinity of weak electrolytes can be found. Weak electrolytes can be found. That is by using Kohlrausch law. So now let us discuss Kohlrausch law. Kohlrausch law of independent migration of ions states that at infinite dilution, when dissociation of an electrolyte is complete, each ion makes a definite contribution towards the molar conductivity of that electrolyte, irrespective of the nature of another ion with which it is associated. Thus, the limiting molar conductivity of an electrolyte. So, the limiting molar conductivity of an electrolyte is represented lambda m naught is equal to lambda m naught of Na plus lambda m naught Cl minus. So limiting molar conductivity of an electrolyte can be obtained by adding the limiting molar conductivities of individual ions. So now let us see the applications of Kohlrausch law. Applications of Kohlrausch law. As we just discussed, the limiting molar conductivity, that is lambda m naught of weak electrolytes, cannot be found directly by using the graph. Therefore, by using this Kohlrausch law, we can find the limiting molar conductivities of weak electrolytes. Therefore, lambda m naught of weak electrolytes can be found by using Kohlrausch law. Lambda m naught of weak electrolytes can be found. We can find the degree of dissociation of weak electrolytes. Therefore, degree of dissociation of weak electrolytes, can be found alpha equal to lambda m by lambda m naught, m naught. So by using this formula lambda m by lambda m naught, we can find the degree of dissociation of weak electrolytes. If we found the degree of dissociation, we can find the dissociation constant also. Dissociation constant of weak electrolytes can be found. Therefore, K equal to C alpha square by 1 minus alpha. C into, what is alpha? Alpha is nothing but lambda m by lambda m naught by 1 minus lambda m by lambda m naught. This can be written as C into lambda m by lambda m naught by lambda m naught minus lambda m by lambda m naught. So here this is whole square. So this can be written as C into lambda m square by lambda m naught whole square into lambda m naught by lambda m naught minus lambda m. So here this is get cancelled. Finally, what do we get? C lambda m square by lambda m naught into lambda m naught minus lambda m. So this is the dissociation constant of weak electrolytes. So by using the Kohlrausch law, we can find the solubility also. Solubility. Therefore, solubility of weak electrolyte, lambda m naught equal to K into 100,000 by solubility. So all these are the applications of Kohlrausch law.